will start this discussion over inertia and momentum. In this first clip, you see that the spinny thing is easy to stop. You can simply put one arm out and stop the spinny thing. In this clip where the speed is drastically increased, it takes two arms to stop it and Alec is dragged. When mass is added while maintaining the speed in the first clip, it takes more force to stop. Alec is dragged halfway around the spinny thing before he can bring it to a stop. This is because of inertia, which is an object's tendency to stay at rest or in motion unless otherwise acted upon. The changes in force needed to stop the spinny thing are caused by momentum. The momentum equation, P equals mv, states that it is directly proportional to mass and velocity. In this video, we demonstrate how manipulating center of mass allows us to accelerate the spinny thing in a constant manner without touching the ground. As you can see, whenever a mass approaches the top of the rotation, the mass starts to move outward, while the opposite moves inward, so as to maintain a center of mass in the downward slant where the gravity accelerates the masses on the spinning thing. Since the force of gravity on Earth is always directed towards its center, the slant of the spinning thing allows for the x component of the force of gravity, or mg cosine theta, to keep the spinning thing spinning. If the center of masses were in the upward slant, the x component of the force of gravity would be working against the masses, slowing down the spinning thing. When we add a third mass, we can more fluidly manipulate the center of mass, as well increasing the overall mass, leading to a faster constant acceleration, as you see here. Moving in and out as you watch the three of us move towards the center of the spinny thing, you will notice that it noticeably accelerates. Conversely, when we move outward, the spinning thing decelerates. One principal component of circular motion is tangential acceleration, which is inversely affected by the radius of the circle. Therefore, our moving inward decreases our distance from the center and increases our tangential acceleration, and vice versa. Another characteristic of circular motion is an object's constant need to move in a straight line. The only factor keeping an object in circular motion is centripetal force. The centripetal forces in these clips are the muscles in our arms and hands holding onto the rim of the spinny thing. We can very simply remove this centripetal force by letting go, demonstrating without a centripetal force, an object will return to a straight path. Every one of us bites it tangentially to our release.
You need more speed than that. Ah.
To demonstrate that the period of a pendulum is only dependent on the length of the pendulum itself and the acceleration of gravity, we went over to the swings. The big boy swings. Since frequency and period are inverse, we can use the first to find the latter. Using a metronome, we tapped out a frequency of 44 beats per minute, which matches nearly perfectly with the frequency of the swing. If we take the inverse and convert minutes to seconds, then we get a period of 1.36 seconds. This is the same for each demonstration. We manipulated the starting height and mass, with each resulting the same 1.36 second period. Also, make sure to be able to keep in mind that these videos are slowed down to measure the frequency and period. The speed of these videos that we converted to is half the speed of original time.
Alright, the video started.
I'm Brandon. Whee!